So just like Dr. Williams, I'm going to talk about simple things. So this is the work that Nicola and Slava has been doing for about a year or so. And when I joined the group of Orel, then I also started doing this type of calculations. So they were trying to develop, okay, so before talking about model, so let's talk about dissociative recombination. So I'm sure everybody already know what's dissociative recombination, because it's explained here, at least in two talks, but just for the sake of completeness. Dissociative recombination is a recombinative process in the entrance channel. So when the electron collides with a positive molecular ion, and dissociative in the exit channel. When the electron transfers its excess of kinetic energy to the vibration of the nucleus, that eventually will vibrate away. So here are some examples of dissociative recombination for the atomic molecule and triatomic molecules. So H2 plus, that has been shown here over and over again, and I will dare to show again the cross-section of H2 plus. I'm also going to show the cross-section for HCO plus and then 2H plus. And here's a schematical picture of the dissociative recombination of the HCO plus when the electron collides with the ion, and the H goes away and the CO goes to the other. So this is so why are you trying to simplify the model? So this is a flow chart of the treatment given for the H plus. This cross-section that has been shown previously by Dr. Newman and previously by two other talks, I believe. And this is a very complicated treatment, so I won't go through the details of that. That's not in the scope of this talk. But to say that using ad initio quantum effects for H2 plus that were not calculated by us, and you use the heterospherical coordinates to describe the system, and slow variable discretization to do a complete diagonalization of the Hamiltonian using the ingredients of MQTT to the closed channel elimination procedure to obtain the physical scatter matrix and the frame transformation to take the scatter matrix from the clamped nuclei configuration to the asymptotic channels where the molecule can vibrate and rotate. And we did all of this, and all of this was done in parallel computes, and it took several hours of calculation, and that was done. It was a long part of my PhD thesis. And then there is also the treatment for HCO plus. That's a little bit. It's yet very complicated, but a little bit more simplified. I'm also not going to go through details of that. The HCO plus cross-section was calculated first by Ivan, and then also Nicola did this PhD thesis, including allowing the CO molecule to vibrate. So what I want to point out from this treatment is that 3 simplifications has already been done. First, the ionic rotation has been neglected. So there is no rotation of the ion in the Hamiltonian. And the second one was already described by Dr. Jungen, the average of the resonances. So the width of the resonance is it's simply inversely proportional to the density of the resonance. So you can average over the resonance. And also the point that was brought up twice today, we are neglecting alkalization. So once the electron is captured, the molecule will dissociate. So as Dr. Newman already said, so they using these 3 approximations, they developed even a simpler model to describe DR that would include mainly the main non-adiabatic couplings for diatomic molecules would be the Young-Taylor, for linear molecules at HCO plus would be the Henneth-Taylor effect. And they also add to this another simplification that was the harmonic approximation, in which in which the molecule would be kept mainly between the ground and the first excited state of the ion, and only populations going only into small vibrations away from the configuration. And this simpler method has been proven to work very well for systems in which non-Oppenheimer effects are dominant. So I'm going to show again the cross-section for H3 plus population. So the green curve there was a calculation that took me months to calculate, and then in a couple of days or weeks, I don't know, they present they have the unconvolved curve, the blue one, and then the red one, the convolved one with the experimental parameters, right on top of the curve that we calculated, and take into account only the couplings, the Young-Teller coupling. And they did the same thing for HCO+, take into account only the Hannah-Teller coupling. And again, the cross-section hits pretty well the calculations of Ivan and Nicholas Mihailov and Duguay. That also took several hours in parallel computer and the NERSC supercomputers. But yet, just to point out, we consider that there is experimental Lapata. I don't remember how the experiment is, but all these theoretical cross sections are about a factor of 2 smaller compared to the experiment. So and now I'm going to give a prescription to how to get this analytical form this simple analytical form for the cross section. So you start with the brackets around the cross sections mean that the cross section is average of the resonance. So you start with the average cross section, and the step function there means that the electron can only the kinetic energy of the electron has to be between the two vibration states, of the molecule, V0 and V1. So the next step is to do a vibrational transformation. We take the scatter matrix calculated for fixed position in the nuclear in the normal mode of the nuclei. And then the next step is to do a Taylor expansion of the scatter matrix in expressing the phase shift of scatter matrix in terms of the quantum effects, and doing also a Taylor expansion of the quantum effect, and getting to the second analytical formula here. So and yet to have an integral to solve there, but doing the harmonic approximation proposed by Dr. Jung, and then the next step would be to simplify this to even a smaller formula, which the only thing that you need to know to calculate your cross section is the frequency of the normal mode omega I and the variation of the quantum effect with respect to the normal mode coordinate. So the mu dq. So you have to take into account also the degeneracy of the normal mode. And so again, the I is in its initial grounded vibrant state, so the electron can only capture between V0 and V1. So using this analytical form, going beyond the Young-Teller coupling, Duguay and Slava, Dr. Green, and then they calculated the cross section. They used this model to calculate the cross section for H3O+. So H3O+. So this is the on the Y coordinates you have the effective quantum number, so proportional to the quantum effect, and the Q2x and Q4x are the two normal modes that you have for the vibration of quanta 1. So you have to take into account these two normal modes, and they're both degenerate. So I want to call the attention here for this part of the picture. So if you take into account only the Young-Teller coupling, that would be, for instance, these two curves here that are degenerate of the linear configuration, and then it splits into A double prime and A prime. You'll be neglecting this coupling here. As you see, this guy here, it's a little bit bented because it reflecting the coupling with this other A prime curve. So they also take into account the coupling between the two states that were not accounted for. And the first section that we have in pretty good agreement with available experimental data. So here we see the first, as also Dr. Jung already explained. So this is an analytical form that's going to drop by the step function every time you hit the vibrational threshold for this normal mode. So here it's one of the normal modes, so it drops here, and then here the second drop is here. And the calculations that has been done, it's only for V1 quantum. We didn't do V2 yet for Dr. Jung. So again, the same thing was done for NH4+, which is a highly symmetric molecule. So here you can see it has three, it's in the TD group, so N H4+ has three triple triple degenerate modes and 2 double degenerate modes. So this is the splitting of one of the triple degenerate modes. And you can see that the pi components are coupled via Young-Taylor splitting, while the S component doesn't couple anything. And so also take into account not only the Young-Taylor splitting, but also the coupling between other states. We can this cross section here with 2 drops. That corresponds to 2 vibrational modes with quantity 1. Also, again, in pretty good agreement with the experiment. The next slide is our new calculation. So we decided to apply this method also for linear systems with dipole moments like N2H plus and HCO plus. So why N2H plus? So besides the astrophysical relevance of N2H plus, to the best of my knowledge, there is no available theoretical DR cross-section, and the only one, the only article that I found was an estimation at higher energies. That and high energies is dominated by the, as I'm gonna show the direct cross-section there. So the high energies is dominated by the direct DR, because already explained by Dr. Huberman and also Dr. Mugen. So just to review, so the direct DR here, the electron is captured directly into the dissociative state of the ion, and then the molecule vibrates away. So this model takes into account mainly the non-indirect DR mechanism, where the ion is captured into excited or double excited state of the molecule, and then it's going to, via non-divided coupling, it's going to couple to the dissociative state of the molecule. And why HCO plus again? So HCO plus is it's a very important astrophysical molecule. It's one of the most polyatomic elements that present in the interstellar. And to try to get a better agreement between the cross sections and the experimental cross section of the literature, we're going to present a work that has a large scale of initial population and a more accurate coupling scheme. So we are taking the natural couplings, the couplings that were taken before in the previous populations, and couplings between not only sigmas and pi's, that was the coupling that I showed for them before, but also couplings between pi's and delta states. So this is the calculation for N2H plus. So we did this for N2H plus. We did this for HCO plus. So we calculate our quantum effects, and this is actually I'm giving the effective quantum numbers for the valence and the reverse states of the nature. So here I want to zoom here on this, just in this line here, and and I want to point out here that the Henner-Taylor splitting is it's a quadratic effect in the normal mode per minute. While the Young-Taylor was linear one. I'll have to mention this one just to show you. So here the Henner-Taylor is a linear effect. So we don't have to extract the dependence of the quantum effect here with respect to Q, but you also have to extract from that what is the Henner-Taylor splitting. Because as if you remember before in the other figures that I showed, the dependence of Q, the normal mode of Q is quadratic, and so is the Henner-Taylor splitting. So to get a coupling scheme for this molecule, it's a little bit more fun. So here's a model of quantum effect a matrix, and that's how we link our ab initio populations to what we are looking for to use in our analytical problem. So the previous populations of HCO plus has been using just this coupling scheme here. We have a bigger matrix here, taking into account all these coupling here, and the zero of diagonal elements are the coupling schemes that at first order approximation in Q. By symmetry considerations, they're supposed to be zero, because we are taking into account only first order in Q. And instead of diagonalizing this matrix to obtain the quantity effects to compare directly with our initial calculations, we are doing a second order perturbation theory. And when you see here that the variation of Q is quadratic, the variation of mu is quadratic with both. And as you have seen in the previous plots of the mu versus mu. Then you calculate the cross-section for an H plot. And before they have published the new results, we are very happy because the cross-section was just on the top of the old. And then that's what I presented them often, and this is the new one, and you try to understand if there is maybe anything missing in the model, maybe the dipole moment is important for these calculations, or maybe, as Dr. Thomas said, maybe the M2H plus has a rotational population, and it's not rotational code as it is the rotational code. That's it. So you can see here the drop. Okay, so this is just deviating a little bit from the simplified model. This is the preliminary result for direct ER and 2H plus. This is just a two-dimensional calculation. We are still doing the calculations to understand the effect of the liberation of NN. So this is for NN frozen, and that's the cross-section that I have. I'm not sure, you cannot see here the lower energy part because it's, in this scale it just doesn't show it here, but it will go over there. So the direct process, happens at much higher energy, and this is here. And I don't want to talk much more about that until we have the 3D calculation. And that's the and we did the same thing for HCO plus, and that's the result that I have for HCO plus. So these are the previous calculations. I didn't have the data of Dr. Newman's simplified model, but they like just above here the calculations of the gain and Yvonne. This is the old experimental Padalak, and this is the new experiment. It's an unpublished data we got from one of the members of the group. And this is our theoretical curve. So one thing that we would like to point out in this curve is that we only did these calculations for HCO plus. We did not include yet the HOC plus. And there could be contamination up to 10% of HOC plus in the experiment. And you see a drop here in this curve at about 120 wave numbers. That will be the vibrational frequency of HOC plus. So we believe that once we add HOC plus to the model, we are expecting to bring the curve a little bit upward here, see the drop coming from HOC plus, and then the curve will continue with about the same order of magnitude here, dropping in the first vibrational model HC plus. So the question is, since especially for N2H plus, you see that the agreement was not as good as expected first. Is there another way to calculate this coupling other than fitting? So this is actually a piece of work for the coupling scheme for N2H plus, where you take into account the sigmas and the pi states, the pi's and the delta states, and they all and you see how much they deflect, and from that you can calculate the coupling, included in the analytical form, calculate the quantum effect. So sometimes this coupling scheme doesn't come out so easy. So the reason we didn't include the HOC plus calculation in cross-sections is because we couldn't come up with a reliable compassing for HCO plus. So is there a better way, but yet equally simplified, to do these calculations? So we are trying that. So instead of using the quantum effects, we're going to go back to our analytical formula and work directly with the schedule matrix. And we've been doing that using the complex method. So we use the schedule matrix that's given by the complex form. And we start by comparing the quantum effects, how good the scheduling calculation that we can afford to do agrees with the initial calculation that we have done. So the initial calculation that we have done, we did in a bigger reference space, and the difference between the reference space 11 to the reference space 9 is about 300,000 configurations. So from here to here, you're dropping all these configurations just because we cannot afford this computation, we cannot afford this calculation. And we see that there is a very good agreement with the quantum effect, so we expect that the cross-section is not going to be that much different. And if you try doing ab initio calculation, with the same reference space, the same base functions and everything, we see that the quantum effects agrees very well with the phase shift of the second calculation. There is a calculation. So doing this calculation, our new cross-section is about 20% lower than the initial calculation. So it's not. I don't know yet why the cross-section is so much lower. It could be due to the fact that we are dropping this 300,000 configurations when we are shrinking our reference space. It could be due to other effects that we don't take into consideration here when you calculate the S matrix, like dipole effects or other interstellar effects that are already included here in the electrostatic potential when we do the initial calculation. And again, how these two cross-sections compare to the experiments is still a mystery for us. So, that's it. Too fast.
Okay, we have plenty of questions.
There's a lot to say, so please questions. I just went through it very fast.
I saw your N2H plus data direct process shows a lot of structure.
Yes.
Why?
This is a time-dependent calculation, so it could be just all the associations of the wave packet before it was out. They didn't do it for your transforming. This cover plotted at 3 o'clock in the morning. That's when it was done. So that's why I wanted to show out of L3, but I don't know yet what it means.
I just want to ask again about the two different experiments. The one was the one that you believe is actually contaminated. Right?
Yes, that was the one that's actually
The
fitting
lower one,
quite
right?
well, yes.
So, so actually, in principle, I mean, the new one is clearly superior, right? You shouldn't really, the old one, you should potentially forget about it, right?
But the dependence is
It's weird. That's, yeah.
new experience.
It depends on the
Look at the fit. She fit it to a, you're supposed to, you roughly say 1/8. That's, when you get really low energy, it should go like 1/8.
Right.
The old experiment went like 1/8. The new experiment goes like 1/8 to the 1.42. So I'm.
Yeah.
And we have quite a few GR measurements that go at other things than 1/8.
Yeah.
I mean, it's not uncommon.
There's a resonance there, threshold.
But there is no resonance.
It's just that the old data, even if it fits nice, it's actually contaminated. So
This curve here also does not go 1/8. The purple one also doesn't have 1/8.
Yeah, but the purple has two components. The purple has two components.
We hope so, yes.
So actually, and the other thing, that there are data on N2B plus, which are not analyzed, but they will hopefully be until a couple of months from now. There are data, all done about me from TFR.
That'd be interesting.
Yeah, and he just says he hopes, he's really busy, but he hopes until the next PR meeting or so they can analyze.
Okay.
Yeah, it took easy to calculate this first section just for the purpose of the H2 plus comes out very fast.
It's nice to hear.
Yeah, I think it's very nice to simplify model because it takes hours and hours and hours. All you do is computation and you can get a pretty reliable cross section. Okay, even if you have at high energies an order of magnitude difference, here where the model should work very, very well, especially because of this average of resonance close to the vibration continuum. We have some of them.
But that's actually quite common. But if we take, for example, HD plus, and we look at the cross sections, HD plus or HD plus, whichever.
HD plus.
Yeah, but we take cross sections measured at all the storage rates. They all differ at low energy.
They're all HD plus.
Yes, they all differ by a factor of 100.
Okay.
The reason is because each of the experiments has different electron temperatures.
Okay.
So below, say 100, below 100 millieV, a factor of, we can understand what a factor of 100 might be. We all meet at 1 eV.
100 milli, I mean, the resolution is typically 1 eV. Right?
No,
So you have
but now I'm
eV.
comparing HD from Astrophysics.
Yeah, okay.
So, right, but we know why that is. So then, of course, in these models, there's no rotation energy included. Maybe we're not really, hopefully we're V equals 0, but maybe we have a bit of V equals 1. And if there's a factor of 10, if you have 1% V equals 1, but the rate of operation is a factor of 100 higher, then in principle they are equal. So
And that's it.
small contaminations may play a big role with low energy.
Yeah, I was also wondering if the dissociative cross-section here is it's much higher because there is an open channel for N plus NH. Is there something going down that way?
You mean N plus X 10%?
Yeah. Okay. So, and could be it could be reflected into the side effect.
I think one of the things that simplified model always has worked for this molecule like compact without dipole moment. I'm not sure if it's direct relation, but for HCO plus and H2H plus it seems to be a bit more complicated. You know, we have like almost 4 dBi of dipole moment, which is pretty big. So I don't know if it's something that like we think about seriously.
It was easier for HCO plus. We didn't think about the dipole moment contribution. HCO plus it was done first because the agreement was pretty neat. And you're expecting that once you include HOC plus, then you can bring this particle over here. But when we saw the new experiment on 2 H+, we thought that when 2 H+ was a soft crowd before, we start thinking about which effects are taken into account, especially when we calculate this first section using the scattering matrix that we don't, the dipole is not included. We don't know how much the dipole is mixing what we call S sigma and P pi waves when I'm calculating this first section here. So for the quantum effect, there was this here. So I'm doing the couplings between the S sigmas and the sigma. So there is by conservation of angular momentum, I want to go delta n equal to plus or minus 1. So sigma and pi and delta, or pi sigma. So we don't know how much of this sigmas and this pi's are coupled by that.
Probably agree that it's worth looking into the rotational structure in theory, if which suggests that maybe there is some rotation excited states, and if there is an effective coupling between rotation and vibration, or let's say redissociation. So then, if rotational structure is involved, then this feature that kind of visible on the experimental world should correspond to rotational kind of constant or rotational levels. What is it? Do you know what the rotational constant is? Which close to 2. Because yeah, there is some feature around 5 MeV or something like this. 5 MeV getting to the resolution of the electron. No, 5, no, below.
So this.
It looks like the feature that Christian was discussing was like a car.
1.5 waves.
Yeah, we won't be able to see anything at 5.
Yeah. Eric, also bring the curve a little bit down here.
I think of the order of Q.
Yeah. The 0 to 1 transition is around a little less than 100 gigahertz, like 90 gigahertz. So it's 2B. So B is 45 gigahertz.
And the nice thing is if you use the scattering matrix from the scattering instead of the scattering matrix from trying to do the quantum defect thing, is that you have the scattering matrix and then you can do the transformation. And Chris, you did that. You did a much carefuler, but for the helium hydride and the lithium hydride, that you actually did the frame transformation. Because once you have the scattering matrix, you do things like that. So that's another thing.
Okay, there is no more questions.